still here. I apologize. I'm not smart enough to figure out how to get my actual picture on the screen here, but ready to go. So, first of all, thanks for everyone who's joined this discussion today. This is, I think, very important topic at this point in time, and appreciate the presentations that have been made so far. I'm going to focus on the vanadium market more specifically, take a look back at some historical data, and talk about some of the characteristics of the vanadium market that are of concern in many areas, and specifically in the flow battery market. Next slide, please. This is just fun and games here. A couple of pretty pictures. The picture on the right is actually a stained glass window in a Ukrainian church here in Pittsburgh. And the picture on the left is the Nordic goddess Freya, also known as Vanadis, who is the goddess of mischievous and fertility, which is quite interesting. Anyway, next slide. Let's talk about vanadium in general, what vanadium is. Next, please. Sorry, next slide, John. Vanadium is a naturally occurring element. It's a transition metal that sits, as we can see here, in the periodic table. Next slide. Vanadium is unique in that it's stable in 4 different oxidation states, and this is obviously a major feature that makes vanadium appropriate for flow batteries. Next slide, please. If we look at consumption of vanadium, roughly 90% of vanadium goes into steel, and there's 2 applications in the steel market. The most important application is HSLA, or high strength low alloy steels, where we make a very small addition of vanadium, typically 0.05% vanadium, and it has a dramatic impact on the yield strength of the steel. The yield strength can increase up to 100% depending on the application and the type of product being made. We also see about 30% of the world's vanadium going into high alloy steels. These are tool steels or high-speed steels where vanadium plays various roles and really has no substitutes. And then we see various other applications, chemicals, oxidation catalysts for production of things like sulfuric acid, catalysts for pollution control, controlling nitrogen oxide and sulfur oxide emissions from industrial sources, and a wide variety of chemical applications. Vanadium is also used in titanium alloys. The workhorse alloy in the titanium industry is Ti-64, which is 90% titanium, 6% aluminum, and 4% vanadium. And you'll find this alloy in turbine blades and jet engines, and structural components of airframes and missiles. And if you're a golfer, your driver's probably 4% vanadium. And then we see some other miscellaneous applications. You see energy storage there at about 1.7% of demand in 2020. Obviously, we anticipate seeing that grow as we look forward. Next slide, please. So just summarizing, vanadium is a transition metal stable in 4 states of oxidation, widely used in producing high-strength steels, used in titanium alloys to create high-strength properties. And vanadium is now, in the very near future, hopefully becoming very important in the energy storage applications. Next slide. I want to address the issue of availability of vanadium, which has been called in question in many forms in the past. This data here from U.S. Geological Survey suggests that at current consumption rates, vanadium reserves globally will supply us for the next 150 years. Next slide. We see vanadium occurring in the Earth's crust, in rivers, in waters, in seas, in the mantle, in the core, in various quantities. But this picture kind of demonstrates the fact that there is vanadium around us all the time. Next slide, please. This picture is interesting. It shows the abundance in the Earth's crust of elements. And what this picture is going to show you is that in the Earth's crust, there's more vanadium than there is chrome, nickel, lithium, cobalt, or any other uh, number of energy storage or battery minerals. So the notion that vanadium abundance is not sufficient to support flow batteries is just completely wrong. Next slide, please. Here's a interesting chart from, again, from US Geological Survey. This is circa 1975, showing vanadium, titanium, magnetite deposits around the world. And the point of this slide is to show you the broad dissemination of reserves of vanadium-bearing minerals in the world. And this obviously is not complete. You can see that this slide doesn't even show any deposits in Brazil, where we have very significant production today. So I just want to try and disable the notion that there isn't enough vanadium in the ground. Next slide. So vanadium is very abundant. We have enough vanadium at current consumption rates to last quite a while. We've seen a lot of projects try to come to market to develop new vanadium mines, and they've had difficulty drawing capital. I think it's safe to say that while the abundance of vanadium is high, it's somewhat unusual to find vanadium present in economically viable concentrations based on historical markets. As we move forward, we discover more deposits, we increase mining and recovery technology, that window opens up farther. So let's move on from this subject. Vanadium consumption in 2020 totaled 112,000 metric tons of V. We can see that China is the largest consumer, followed by Europe, North America, and other countries. If we put up a picture here of steel production by country, we'd probably see a very similar pattern here, given 90% of the vanadium consumption is occurring in the steel industry. And obviously, China's the largest steel producer in the world today. Next slide. Looking at specific vanadium consumption rates, that is, how many kilos of V are consumed per ton of steel produced on a global basis, the average is 0.06 kilos of V per ton of steel produced. But you can see that that specific consumption rate varies widely from country to country. And what we do see over time is that the developing economies, where the need for infrastructure to support economic development occurs, we see specific consumption rates of vanadium moving up fast in those countries as people recognize the value proposition here of using high strength, low alloy steels as opposed to lower strength carbon manganese steels to build out infrastructure necessary to create economic opportunity. So the global average is 0.6. Here we see China at 0.62. If we go back 10 years ago, China was probably on par with India. So we can see the massive change that's occurred in China. And again, we see that occurring in India and other parts of the world today as well. Next slide, please. Looking at consumption over time, we can see the trends here, and obvious trend here is what's happened in China, going from a very small consumer in 2001 up to a very, very, very large consumer of vanadium in 2020. Next slide, please. Here we have just some comments from our friends at the China Iron and Steel Research Institute, which is an organization that, among other things, is very focused on driving increased utilization of vanadium in the steel industry in China for economic benefit for China. In China, the steel reinforcing bars used in concrete construction are the major application for vanadium. And we see that the production of this steel is reaching new highs this year. And as a result, consumption of vanadium in China is reaching new highs. And we also see that consumption of vanadium, in this lower part of the slide, we can see the data of what impact on vanadium consumption has occurred as a result of the steel production in China. Next slide, please. This is just showing the trend in crude steel production in China. You see this sawtooth pattern where in February of every year, production drops dramatically due to the national holiday and rebounds later. But you can see the long-term trend here in terms of steel production is quite strong up. Next slide, please. And mirroring that is the rebar production. We can see here that post-COVID in China, which was really second quarter of 2020, rebar production reached all-time highs. And more recently, in May, again, we've broken the record for rebar production on a monthly basis. And that, of course, translates directly to vanadium consumption. Next slide. Let's look at a forecast for consumption. When we look at vanadium consumption, typically the drivers to changes in consumption is the major drivers, the change in steel production on a global basis, and the secondary driver is the change in specific consumption rate of vanadium in those countries. And now with the advent of the VRFB, I think a third and important driver obviously is what goes on in terms of consumption of vanadium in energy storage applications. Next slide, please. So we assume that we're going to see about a 2% compound annual growth rate in steel production going forward. There's other forecasts out there. I think they're all within a 0.5% or so, but our forecast that we're going to use for projection consumption growth is 2% for steel production globally. Next slide, please. So with that assumption, we can see what happens here. Global steel production of 1.8 billion tons in 2021 reaches just short of 1.9 billion tons. Sorry, that was 2020. In 2021, 1.9 billion tons, rising to just over 2 billion tons in 2025. Next slide, please. Here is our projected change in vanadium specific consumption rates. The trend in the world outside of China is forecasted to be rather moderate and on par with what we've seen historically. In China, we can see the rapid rise in the specific consumption rate from 2016 to 2020. And our projection is that that curve will flatten out. We'll continue to see the specific consumption rate go up, but not at the rates that we've seen in past years, as today, essentially all the rebar being produced is consuming vanadium, which was not the case prior to 2018. Next slide, please. So here's my stab in the dark at a forecast for vanadium consumption in VRB applications. And there's plenty of people out there making projections. I think it's very difficult to project demand in a new market with new technology. But this is my forecast. We can see consumption reached a relatively high point in 2017 and decreased from there in line with changes in the vanadium market. And we can see here a very robust forecast. I imagine some people on this meeting may have different ideas here, and happy to talk about that. Next slide, please. So we roll up all of these issues and make a projection here for vanadium consumption looking forward. In 2020, consumption is just about 112,000 tons of V. And here we show that rising to as much as 170,000 metric tons of pure V by 2025. Next slide, please. So here's the data, just looking at the changes. You can see the majority of the change that we forecast here is from energy storage applications. And second, but very important source of new demand going forward continues to be China, and some moderate growth in other parts of the market. Note that the energy storage number here is an over-the-top number for all regions rather than trying to parse that out into each region. I think that the finer you try to divide this data, the less accuracy you see. Next slide. Now let's talk about production. In 2020, we saw production at 114,000 metric tons of V. The source of vanadium production, about 68% of vanadium produced in 2020 was vanadium recovered from slag generated in steel mills in Russia, China, and one small steel mill in New Zealand. This co-product steel slag is obviously the predominant source of vanadium production today. About 18% of production in 2020 came from primary mines, and we in essence have three of those, one in Brazil, the Largo Maracás mine. In South Africa, we have the Bushveld Vametco mine and the Glencore Rovan mines. There are a couple of very, very small primary vanadium mines in China as well, but we don't include those in this picture because they're frankly, they're just too small. And then the third leg here is what we call secondary units. This is vanadium recovered from waste generated in either refining oil that contains vanadium or burning that oil in power generation stations. And in those processes, you're going to generate a boiler slag or ash or a spent catalyst or some sort of residue or pet coke ash at the end of the refining process where the vanadium will concentrate. And those materials are used for production of vanadium and contribute about 14% of the supply in 2020. Next slide, please. We look at the slag supply, and again, you can see China dominates here, and you can see how the supply of vanadium from slag and steel mills in China grew dramatically, really from 2005 to 2015. And when we saw the market situation tighten up in 2018, again, we saw an increase in vanadium slag production in China being driven by the market situation. So production of vanadium from slag has grown from just over 20,000 metric tons of V a year in 2001 up to about 75,000 tons of V a year in 2020. Next slide. If we look at primary ore production, we see that if we look back in time, South Africa was a very large producer of vanadium from primary ore. That production in South Africa took a hit when Highveld Steel and Vanadium went into business rescue. We've seen some recovery in South Africa. In China, we see the very high production from stone coal in the mid 2000s, again associated with a tight market condition that allowed that relatively high cost production to come into play. And again, we see in 2018, given the market situation, that source of material moving up. And of course, we also see in this chart the increases in production coming from Brazil as Largo has brought the Maracás mine online really in 2015. Next slide. This is a look at what's happened in terms of supply of vanadium from stone coal. This is a carbonaceous shale material that's found in many provinces in China that contains on average something less than 1% V2O5. And there are various generations of technology to recover vanadium from these sources. I do consider these sources very high cost and more or less swing capacity in the market. And when we have very tight market conditions, we see production in these sources moving up. And when markets are more imbalanced, we see less production coming from the Chinese stone coal. Next slide, please. Secondary vanadium production. Again, this is vanadium coming out of the ground in oil, and that oil is either being burned in a power station or it's being refined. And the vanadium present in the oil is concentrated in waste products that are bought and sold and used for production of vanadium. Interesting, you can see the surge here in 2019 and 2020, and I think going forward, we're going to continue to see an increase in secondary vanadium production for several reasons. Next slide, please. So when we put all these raw materials on top of each other, we can see that the slag co-product is the most important source of vanadium today and has been growing dramatically. production from primary ores has seen some ups and downs, but been relatively stable, and secondary materials have been relatively stable until the last couple of years when they've moved up significantly. Next slide, please. And looking at vanadium production by country, here we see again China dominating the picture as a result of the massive amount of vanadium-bearing slag coming out of the steel mills in Hebei and Sichuan provinces primarily. Of course, we also see Russia producing vanadium, South Africa, Europe, Brazil, and North America as important contributors to the supply base. Next slide. So if we look at the historical data here for production, we can see the trends here. Again, China is the most important producer, and everybody else is way down the list in terms of contribution to global production. Next slide, please. Sorry, can we go back, John, for 1 second? Just want to bring your attention to the bottom line in this chart, ex-China production. And you can see that, while the vanadium market production has grown by, I'm going to say about 65% over this period, the vast majority of that has been in China. Outside of China, we've seen a rather modest increase in production over these past 11 years. Next slide, please. So again, supply of vanadium is very closely related to the generation of slag from these steel mills. Production from primary ores has returned to 2008 levels as Largo's come up online. Stone coal-based production has recovered, and I think will continue to be cyclical depending on markets. And secondary sources have grown significantly as there's a strong focus on recycling industrial waste. Next slide. Looking forward, the assumptions that we bake into the production forecast is relatively strong market, supporting ongoing ramp up of Chinese slag-based production from 62,000 metric tons of V in 2020 to 78,000 metric tons of V in 2025. And this is really utilization of capacity that's not being utilized today. One good example is Chengda Steel, who have a massive blast furnace that for 3 years they've been trying to get up and running. They haven't stabilized the operation. If and when they get that blast furnace up and running, their vanadium slag production will increase pretty significantly. The stone coal production, again being swing capacity, should be there to supply growing demand that we see. We do expect to see some modest capacity increases at some existing producers going through debottlenecking exercises. And really, we also see significant growth in the next few years coming from secondary sources. And this is really the result of a change in the sulfur content of bunker fuel. The International Maritime Organization has altered the specification to lower the sulfur content in bunker fuel by an order of magnitude. Today, bunker fuel is basically the heavy bottoms coming out of the refineries blended together to be burned in vessels transversing the oceans. And this new regulation, which is obviously designed to reduce sulfur emissions, has a huge implication. Today, those heavy bottoms can be used, but going forward, those heavy bottoms are going to have to pass over a catalyst to desulfurize that material before it can be used for bunker fuels. So as a result, we're going to see a real surge in spent catalysts, vanadium-bearing spent catalysts coming to market in the next few years. The regulation's gone into effect, and over the next couple of years, you'll start to see the refineries dumping their catalyst beds as they become inactive, and we're going to see more and more vanadium coming from those sources. And it's a relatively short timeline to bring that new vanadium to market. You need a refinery with a investment that's not the scale of a vanadium primary mine. and the units are going to be available there with essentially zero or maybe negative raw material costs. So we should see some significant growth in relatively low cost vanadium production from those sources looking forward. Next slide. So our forecast suggests that we're going to see vanadium production grow from 114,000 tons in 2025 to 165,000 tons in, I'm sorry, 114,000 tons in 2020 to 165,000 tons in 2025, or almost 45% increase in production. Next slide. Here we see the production changes by country. Again, you see continued growth in China being the dominant picture that we're seeing here. Next, please. Now let's roll this all up and look at what this forecast tells us. We can see in 2020, vanadium production outstripped consumption by about 2,000 tons of V, but pretty well matched. This forecast miraculously shows those two lines laying almost on top of each other going forward until we get to 2025, where the growing demand runs over the production forecast here. Next slide, please. Taking that forecast and history and just looking at change in inventory on an annual basis, you can see what's happened here. We can go back to 2018 and see the huge drawdown in inventory that really disrupted the market, stimulating new production, which resulted in some inventory increases in 2019 and 2020. And our projection is 2021. We're going to see a deficit again, and really going forward, we're going to see challenge to see supply meet demand to some extent based on this forecast. Next slide, please. Let's look at some historical data. This is the Metal Bulletin V2O5 monthly midpoint average price, and this is the index that a lot of people that buy and sell vanadium, typically in the chemical and titanium space and in the energy storage space, will look to this as a reference. What you see here is a very painful curve with some incredible price spikes followed by protracted periods of relatively low prices. When you roll this all up, you see an average price on an inflated basis over the last 17 years of close to $8 per pound of V2O5, with a median price of something below that, $6.60. And the next slide kind of looks at this data in a different way. This is a price distribution chart. So what this chart is showing us is that the predominant price is $6 to $7. It's more often $6 to $7 than it is any other price range. If the world was perfect, you'd see a very perfect distribution here. But what we really have is a bimodal distribution here with a main peak at $6 to $7 and then a secondary peak at $15 to $16. And I do believe what this is demonstrating is that in a normal world where supply is in excess of demand and cost of production drives the market price, that $6 to $7 price is a pretty important number. When we get into environments where supply can't keep up with demand and markets are extremely tight, we see this $15 to $16 price having some stability. And when you get above that level, there is no stability. You see massive loss of demand due to substitution in the steel industry, trying to use niobium or niobium plus titanium to replace vanadium. And you simply don't see, the data doesn't show any stability in prices above that level. So I think this is an important picture if you're trying to understand the vanadium market. Next slide.
Jerry, just got a couple more minutes left here.
Yep. This slide kind of looks at the price spike we saw back in 2005 and kind of overlays the last few years on that trend, and you can see some very interesting parallels there. Next slide.
Oh, sorry.
That's all right. Here we see in China, V2O5 prices have crept up really from November through to July 21st. I think today we've seen that price actually back down about 5 or 6 cents in China. But over the past 7 or 8 months, we've seen the markets tighten up quite a bit, I think, reflecting the fact that we see some deficit in supply versus demand this year. Next slide. And this is simply looking at the change in prices over time in China, FOB China, and in warehouse Rotterdam. And you can see as we sit here today, those numbers are, I'm sorry, for June averages, those numbers are very close to each other. Next slide. That's it. That's it. Apologize for the long slideshow, and happy to try and answer any questions.
Yeah, I think we have time for just a couple. There is one in the Q&A. Terry, you state that there is enough V for the next 150 years at the current rate. The issue is that the rate of V demand for VRFB will increase exponentially if it's successful. Thus, is the current rate a good reference? Is all the V mineable?
Yeah, well, I think, what we've said here is that there's plenty of vanadium in the ground. And if you look back at what's happened, the consumption and production of vanadium have grown dramatically over the last 20 years. And the fact is, when the market justifies it, there's plenty of vanadium out there to come to the market. The real issue is the short term. If you want to develop a new vanadium primary mine, it's typically 5 years from construction financing till first production, and then it's typically another 18 months from first production until the plant reaches full capacity. So there's a long lag time to bringing new supplies online from primary mine projects. But there's a lot of them out there that if they can draw the capital, they can produce a lot of vanadium. And the second point I'd make again is the fact that we are going to see fairly rapid and significant increases in supply from secondary sources. So yeah, I think, it's anybody's guess as to how much vanadium flow batteries or other energy storage applications, which I don't want to discount because there's a lot of work going on in utilization of vanadium in cathodes of lithium ion systems and next generation intercalation batteries based on calcium or magnesium, which will require vanadium cathode materials. So there's a lot of opportunity out there for vanadium. There's a lot of vanadium in the ground. And if you look back in time, somehow the supply has increased as the demand's increased. The time lag there is what causes us these price spikes. You see the price take off, the market supply improve, and then we see the market return to a normal condition, typically within about 18 months when we have one of these price spikes.
And one final question, Terry, maybe it can just be a quick answer. Do you have a guesstimate on what is the percentage of the current vanadium production that's classified as, quote, high purity or usable for VRFBs?
Well, that question requires an hour or so of answer. The first question is what's required for VRFBs, and I think you'll get different answers depending on who you talk to. In my view, we obviously need very high purity electrolyte, and to the extent we can produce high purity oxides to convert to electrolytes, I think that's important. So without being able to look at all the specs and understand specifically what the battery guys want, before this market showed up, we'd say that about 5% of the supply base is, quote, high purity vanadium. And again, high purity means different things to different people. In Hot Springs, Arkansas, US Vanadium's producing material that's 4 or 5 nines purity all day long. Other people will consider anything above 98%, which is the commodity grade spec, as high purity. So it's a difficult question to answer.
All right.